Hello and welcome to Rational Expressions. We're going to be taking a look at section 1.4 for TCNJ's MAT096. So a rational expression is basically exactly what the name implies. An expression is basically anything without an equal sign, so 2x or x plus 1, and rational means that there's a fraction. So when you have one of these guys, it is a rational expression. They behave by and large identical to regular numbers in algebra that you've worked with before. It's just they have the complications of being fractions. One big no-no when playing around with these guys that you've got to be on the lookout for is dividing by zero. Dividing by zero is strictly forbidden in mathematics. It's not allowed anywhere. If you allow me to divide by zero, I can unhinge mathematics by making 1 equal 2. And then math as we know it is completely forfeit. With that in mind, we're going to play around with the domain of these statements. So the domain in this problem is playing around with possible x values, the range being y values. What's tricky about these problems is technically the domain is infinite. There's all bunch of numbers that work for this problem, and if you were just trying to list the right answers, you could spend the rest of your natural life and still not hit them all. So instead we try and focus on the last slide, which was talking about dividing by zero. Instead of trying to list all the right answers, I just want to list the wrong answers. So the domain can be anything you like, all real numbers, except negative 1. Say negative 1. So any number you want for x except negative 1. Why is negative 1 bad? It makes the bottom equal 0. So it's a strict no-no. Here it's a little bit uglier. I've got a quadratic to deal with. Remember the rules for quadratics. I want to add to the middle and multiply to the end. So if I want to make 7, I need 1 and 7. Because I'm trying to make a positive 6, I'll keep my 7 positive. As it turns out, positive 1 and negative 7 are the troublemakers. So I could also just say x cannot equal 1 or negative 7. Anything else you like, decimals, fractions, anything's good except 1 and negative 7. So here we're trying to simplify. Math loves to talk about solving and simplifying. They're really the most popular directions you ever pick up. Simplifying is basically just reducing this fraction, just like you would with regular numbers. To do that, I want to factor the top and the bottom. The top, I'll pull out a 2. Bottom, I don't like this 4 out front, so I want to try and pull him out front first. Take the extra step of actually writing this out, just so that I don't make a knucklehead mistake. Now I want to make my 2 parentheses as if I'm factoring just like before. Add to negative 5, multiply to 6. So it's going to be negative 2 and negative 3. These x minus 2's cross out perfectly. Be careful. It's a very tempting mistake. Students will say 2 over 4 and they'll just reduce right off the bat. If there's pluses or minuses involved in the problem, they block you from factoring that out. You can only factor when the thing you're crossing out is being multiplied by other things. That way it's actually a factor and you're reducing it. This is a term that's a little bit different. 2 and 4 can reduce here because they're being multiplied. My reduced answer is 1 over 2 times x minus 3. That's my solution. Now, this is quite a bit scarier, but it's the exact same math. If you want, you can FOIL out the top and the top and end up with one big monstrous polynomial, but then the next thing you're going to do is factor that monstrous polynomial. So why bother pushing it all together? Instead, just factor each of the pieces. You can pull a 3x out here. Down here on the bottom, this is a difference of squares. It's a nice one to know. A squared minus b squared is always going to factor into a plus b, a minus b. It's a very handy one to be aware of. So here I got myself an x plus 1, x minus 1. Up here, it's just a classic quadratic. Add to the middle, multiply to the end. And down here, there's really nothing to do, so we just leave it as is. When I cross out, so long as I cross out bottom and top, it doesn't matter if it's the same fraction, different fraction, I don't care, so long as it's a bottom and top. There are no other parentheses that cross out, so I'm going to make this x squared just an x, and this x with the 3 go away. My final answer ends up being 3 times x minus 3 times x plus 2, all over 4x times x minus 1. As far as I'm concerned, that's the best answer. Some people just feel obligated to FOIL this together and distribute a 3 in, but why? Let's what's nice about the factored answer is if I missed a factor somewhere along the way, it's staring me in the face. If it's all four together, I'm not even going to notice that. Okay, so this problem helps a lot if you know how to work with basic fractions. If you use a calculator to do this all the time, you've probably forgotten this skill. You might have to remind yourself of elementary school. 2/3 plus 3/4. If you were to try and do that officially without a calculator, the trick is to get a common denominator. So I'd multiply here by 4 and 4, and multiply here by 3 and 3. That way I'd get everybody over 12 and life would be good. This problem's the exact same logic. It's just a little bit scarier with letters mixed in. My common denominator is x minus 1 times x plus 2. So I need an x plus 2 on top and bottom. Which gives me 3x plus 6. Just like in the last problem, I'm not going to bother multiplying these two together. I'll just leave it like that. This other guy, I need an x minus 1 on top and bottom. X squared minus x over x plus 2 times x minus 1. The order is different of the two fractions, but 3 times 4 is the same thing as 4 times 3, so who really cares? So what I really want to do is add the numerators. Just blanket them all over top, that one shared. And again, order does not matter. I have no x squared to pair up with. I have a 3x and a negative x. I have a 6 with no partner. So that's my numerator. Now, if I could factor the top, I would try. Not because I like the answer better that way, even though I do. Instead, I'd try and factor the top to see if stuff crosses out. But in order to multiply to 6 and add to positive 2 with everybody being positive, it's just not going to happen. Okay, so now this is a whole different animal. This is a fraction within my fraction. A fraction within my fraction is big trouble. They're really annoying, and you've got to deal with them. Again, going back to basic fractions, depending on how you work with them. If you were to take this problem, and a lot of people in my school like to use keep, change, flip, you keep the 2/3 how it is. You change the division to multiplication, and then you flip the bottom guy to 5 over 4. At that point, it becomes like the other problem, and you can reduce as necessary, multiply top, multiply bottom, you got an answer. It's totally legitimate, except in this problem, it's pretty annoying, because this is not an easy addition. This is not an easy subtraction. Once you do all that work, you got to keep, change, flip it. It's kind of a nightmare. It's much easier, and a little bit faster, to look at the common denominator of this problem. You've got a y, and you've got an x. Your common denominator is yx. Multiplying that up top, maybe I should write that as xy. X over y times yx, the y's cross out, and I get myself an x squared. Down the bottom, I get myself a yx or an xy, but it doesn't matter. My x's cross out, and I get a y squared. That's a minus. I see I can factor out an x up top. I can factor out a y on the bottom. It turns out that wasn't really necessary because nothing crosses out. I like to push it that extra step just to see if stuff crosses out, but it wasn't really needed. This is my problem. Alright, so now this one's a little bit misleading. This classic division sign, for whatever reason, it's a little bit harder to comprehend. I prefer to rewrite the problem like this, just so it kind of feels better. Oops. That was rather optimistic of me. Problem would be a lot easier with that writing. Alright, so like before, I'm going to get myself a common denominator of xy. I'm going to blanket, multiply through everybody by that. Down the bottom, I get myself an x squared plus y squared. Now here I have a rational expression and just this lone x. In order to subtract them and combine them together, I need a common denominator. So I'm going to multiply this guy by x squared plus y squared over x squared plus y squared. I get myself x cubed plus xy squared. And then I might as well just combine that with the xy squared on the other one over x squared plus y squared. Please be careful, this gets a lot of people into trouble. When they do that subtraction, they remember to combine these together, but then they forget that this is being subtracted. So that's actually a negative xy squared, not positive. I've got an xy squared and a negative xy squared. They just cancel. My final answer is x cubed over x squared plus y squared. Alright, now this one's just frightening. It's a very daunting problem, and it's kind of trying to entrap you into trouble. A lot of people would see this, and they would start to take x plus 6 times x plus 6 times x plus 6 times x plus 6, and they'd expand it. You'd end up using an entire sheet of paper and get completely lost in a sea of algebra, and there's really no hope. Instead, focus on what you should be looking for in the problem. I've got a 3-year-old who they like to encourage me to get him thinking math, and most PBS shows would say, oh, math is just about numbers. Let's make sure he knows how to count to 10. That's horrible. Math is not about numbers. Math is about identifying patterns. The pattern here is that we've got an x plus 6, an x plus 6, and an x plus 6. Those 3 statements, it can't just be a coincidence they were in the problem. So what I want to do is, I want to divide top and bottom by x plus 6 to the 3rd. I chose to the 3rd because that's the lowest exponent of the 3. So up here I get a 2x, 3 of those 4 x plus 6's go away. Over here all of the x plus 6's go away. And on the bottom, if I have 8 and I take 3 away, I'm left with 5. And the problem just got significantly easier. There's still an exponent of the problem, but that's on the bottom and it's not really hurting anybody. Up top I can distribute that in. Combine some like terms. I could factor that top, but that's not really going to yield anything, so I'll just leave this as my final answer. Alright, last but not least, we're going to rationalize the denominator. If you encounter something like this, rationalizing the denominator is easy. You multiply top and bottom by that square root, and you fix your mistake. Square root of 2 times square root of 2 is square root of 4, which is just 2. This whole reason for this is the official math people tend to have a couple of hang-ups. They don't like those fractions in the fractions, they don't like negative exponents, they don't like square roots in the denominator. It's just not pure. So what we're trying to do here is make this square root in the bottom or leave. It's allowed to be in the problem, it's just not allowed to be in the bottom. That's a bad answer. If I just multiply top and bottom by root 2, it doesn't work out as nicely as this because of that plus sign. So instead, I'm going to call on the help of my complex conjugate. Oops, that's a J. Complex conjugate. Complex conjugate is the exact same thing as the bottom, with one slight difference. Instead of having that plus in the middle, we're going to put minuses in the middle. Up top, nothing awesome happens, but then on the bottom, if I FOIL that, I get 1 minus root 2 plus root 2 minus the square root of 4, or just 2. And lo and behold, I get a negative root 2 and a positive root 2, and they completely disappear. The reason this works is because of the difference of squares we saw earlier. We're purposely creating a difference of squares situation to make those roots cross out. I just got a 1 minus root 2 over negative 1, 1 minus 2, and I get negative 1 plus root 2. And there you go. The radical is out of the bottom, and we got ourselves an answer. Alright, I hope you enjoyed.